What are you demoing today?
Today I'm demoing the work that I do here at Microsoft Research on predictive models of forest dynamics. So let's put that in a little bit of context. Forests are really important in a number of ways. They harbour 2/3 of global biodiversity. They are the only source of fuel wood for 2 billion people on the planet. But also trees are made of wood, and wood is made of carbon. And the world's forests are actually a huge store of carbon. They store as much carbon as is currently in the atmosphere. So the way trees grow and suck carbon down from the atmosphere and then die and release that carbon back into the atmosphere is actually hugely important for the future of the global carbon cycle and hence climate change. In fact, it's currently the single largest source of uncertainty in the future of the Earth's climate. So how do we go about building a predictive model of forest dynamics? You know, we need those predictive models in order that we can anticipate the effects of our actions in the way we manage forests and to predict the future of the forest carbon cycle at global scales. And really, the answer to that question, how do we build those predictive models, is in the question, which is that we need to think about forests as a collection of trees. And if we can only understand how those trees grow and how they die, then we can understand how the forest as a whole develops. So what we do, the first thing we do is we go back to the forestry literature, and we find that foresters have done an incredible amount of work identifying what determines how trees grow and die. We now know that trees in the understory of the forest are driven by the amount of light that is incident on those small understory trees, and we know that the way that canopy trees grow and die is determined by how much space they capture in the canopy. So all we need then is the ability to predict the incident light level on small trees and the exposed crown area, that is the space captured in the canopy for large trees, and then we can then in turn predict growth and mortality, and off we go and we have our model. And that's what we have. We have a model called the PPA, and I have a couple of slides here briefly, and if you can just see that very briefly. The PPA takes a limiting assumption. It makes trees infinitely intelligent. And paradoxically, when we make trees infinitely intelligent, everything gets very simple, and we're left with a model that predicts ECA very, very quickly and rapidly. And we find that that model fits observations extremely well. So I'm just going to very briefly show you a visualization of that model here. What we're looking at here is the dynamics of a forest left to its own devices. As we start, this is a young forest at age 5 years or so, and over 100 years we see as the trees are getting larger, we're seeing this so-called Z-star move up, we're seeing the build-up of an understory. And if we look especially top down, we can see we start with a large number of small trees. These trees grow to become a small number of large trees, and we see changes in the species composition here. I'll show you that here. So initially, all the species do equally well, but as we go forward through time, we identify a clear set of winners and losers called ecological succession. So in a nutshell, what we have is a model that seems to work and is useful for guiding management and addressing forest carbon, forest biodiversity, and optimal silviculture and logging. Thank you.